Okay, folks, welcome back to the VAS Home Mathematics Studio, where I'm putting together another video for you. This one, we are starting chapter 5, which is about kind of this umbrella term of other functions. So we're going to see some crazy stuff in this chapter. We're only going to be looking at section 5.1, 5.2, and 5.3. We're going to start with 5.1, which is about function composition, also known as composite functions. So you'll hear me refer to functions in this section as, that's a composite function. And we'll start with an example. Example number 1 here says the surface area S of a sphere is a function of its radius r and is given by the formula S of r equals 4 pi r squared. Well, that's the formula for the surface area of a sphere, 4 times pi r squared. Suppose the sphere is being inflated so that the radius of the sphere is increasing according to the formula r of t equals 3 times t squared, where t is measured in seconds, t is greater than or equal to 0, and r is measured in inches. Find and interpret s of t. Okay, so s of t, the first thing I notice here is it's s of t, not s of r. This function is giving me surface area as a function of the radius, but they want surface area as a function of time. So let's go ahead and see how this would work out. Surface area as a function of time, well, it's going to be 4 pi times the radius squared, and we have radius as a function of time. So this is going to become 4 pi times the function for r, which is 3t squared. But that whole function is squared because r is squared in the original surface area function. This is going to give us 4 pi times 9t to the 4th, which we can simplify as, assuming we can keep the page width where we need it to be, we can simplify that as 36 pi times t to the 4th. And that is surface area as a function of time. So we're asked to find and interpret s of t. Here is s of t. Now let's interpret it. So for this case, s of t is the surface area of a sphere as a function of time. It's not the surface area of any sphere. It's for this particular application. Okay, let's move on to the next part here. It says describe what you just did with the functions s of r and r of t to get s of t. Well, basically, we plugged in r as a function of t for radius in the function s, surface area as a function of radius. That's all we did. We plugged one function into another, and we got what is, from now on, we'll call a composite function. Okay, so basically a composite function is when we plug one function into another. And let's kind of formalize that here with the following definition. So folks, there you have the definition of a composite function. The composition of f with g, written as f composed with g. So this little circle here, it's not the word fog, folks. It is f composed with g. It's defined by the formula f of g of x. So g of x is the input to the function f. And just a little diagram here to kind of represent that. If we start with x values, so we'll take some value of x in the domain of the function g, and then we do g, whatever the g function is to that point, to that x value, what we get here is g of x. And then if we take that value from g of x, that output, and we plug it into the function f, we get f of g of x. So the output of g goes in as the input of f. And this whole thing right here, if we take it directly from here to here, is f composed with g. That's the notation. And again, you will hear me most often say something more like this more often I'll say, hey, that's a composite function than a function composition. Okay, let's look at some examples here. In example 2, we are given f of x equals x squared minus 4x, and g of x equals 2 minus the square root of x plus 3. And then we have this little rational function here, h of x is 2x over the quantity x plus 1. Find and simplify indicated composite functions and state the domain for each. Let's go ahead and look at f of g of x first. So just quick note as I get started here on this one, you'll notice that anywhere I see an x in the original function for f, I have input g of x into that place. So I've taken that function g of x and I've input it there, and I've also input it there. So that gives me this expression here, which I'm going to go ahead and simplify right now. All right, folks, there you have it. F of g of x is, it's not x equals 1. That should be x minus 1, because I get 4 plus 3 is 7. I have the plus x, the minus 8. 7 minus 8 is negative 1. So let's talk now. This is our composite function. Let's talk about the domain. So as written, x minus 1 has no domain restriction. And you're tempted to just say, yeah, that the domain is all real numbers. But we have to remember what went into f of g of x. We have to go back and look at the domain for g of x, because that was the input to f. F has no domain restrictions because it's a polynomial. But g of x is a square root function. So we have to make sure that for our domain we consider any domain restrictions in the original. So the domain of this is going to have to be x plus 3 is greater than or equal to 0. That means x is greater than or equal to negative 3. And that is based on the domain of the input function g of x. Okay, that's great. So let's take a look at the next one, part B here. A little bit trickier. This is h of x. So I'm going to go ahead and write that out for you, then work on simplifying it. We have h of x. So anywhere I see x in h of x, I have to plug back that rational function in there. So this is going to be tricky. So let's see what this looks like. I'm going to have 2 times the quantity 2x over x plus 1 divided by x plus 1, and x is going to be 2x over the quantity x plus 1. So again, I want you to notice here that wherever the x's are, that's where I had to plug h of x back in. Now let's go ahead and try to simplify this thing. All right, there's our simplified version of h of x. We have 4x divided by the quantity 3x plus 1. Now let's talk about the domain. Okay, so the domain on this one's a bit trickier. We're going to have to go back and look at some of the things in the original function. So let's take a look back up here at, let me erase some of these highlights up here so we can talk about some fresh stuff. Okay, so taking a look at the original function h of x, I know that that's an input to my composite function, and I have a denominator of x plus 1. So from the original function, x plus 1 cannot equal 0. And again, I just want to make note, this is from h of x, which is an input to the composite function. So that means x cannot equal negative 1. Okay, x cannot equal negative 1. But there's more than that. So let's go back and look at, let's plus 1 there. Let's go back and look at our original work for h of x. We had this denominator here. We had 2x over x plus 1 plus 1. And let's see what happens when we look at that, because that is a denominator. We cannot have that equal to 0. So if I say 2x over x plus 1 can, excuse me, I forgot the plus 1 part there. If that cannot equal 0, let's see what happens here. Well, we've got, this is going to become 2x over x plus 1 plus x plus 1 over x plus 1. So I'm just turning that 1 into something that has a common denominator with the piece on the left. And that's going to equal 3x plus 1 over the quantity x plus 1. And that cannot equal 0. So in order for that to not equal 0, we just have to look at that numerator. 3x plus 1 cannot equal 0. So that means 3x plus 1 cannot equal 0, or x cannot equal negative 1/3. Okay, so there's our two domain restrictions, and this is this piece here that comes from h of x. And if you'd look back into our simplified composite, you'll notice it has a denominator of 3x plus 1. We could have just looked at that there and said, yeah, x cannot equal negative 1/3, but I wanted to show it to you two different ways. So this one, if we were to, WebAssign may ask you to enter that in interval notation. Let's take a look and see what that looks like. So if I have my number line here, I am going to, well, let's be real, we don't even need a number line for this. We can just say that the domain for this is everything except negative 1 and negative 1/3. So that's going to be from negative infinity to negative 1, and from negative 1 to negative 1/3, and then from negative 1/3 to infinity. So there is our domain for that h of x function. All right, folks, let's continue on to page 2 now.